Welcome. In this video, we'll walk through a series of math problems, covering a variety of topics that are common in standardized tests like the SAT. Our goal is to break down each problem step by step and solidify your understanding of the underlying concepts. By the end of this session, you will be able to solve composite function problems, apply percentage calculations, work with ratios, interpret scatter plots, solve for constants in function transformations, and much more. Let's begin with our first problem, which deals with functions. We are given two functions, f of x equals 2x squared minus 5x minus 3, and g of x equals the square root of 6 times f of x minus 9. The question asks us to calculate the positive value of g of 6. This is a composite function problem. We need to evaluate the inner function, f of 6, first, and then use that result to evaluate the outer function, g of that result. The objective here is to correctly perform function composition and evaluation. First, let's find the value of f of 6. We substitute 6 for x in the expression for f of x. So we have f of 6 equals 2 times 6 squared, minus 5 times 6, minus 3. Following the order of operations, we calculate 6 squared first, which is 36. So we have 2 times 36, minus 5 times 6, which is 30, minus 3. This simplifies to 72 minus 30 minus 3. 72 minus 30 is 42, and 42 minus 3 is 9. So f of 6 equals 39. Now we can use this result to find g of 6. Notice that the definition of g of x involves f of x. Therefore, g of 6 will involve f of 6. So g of 6 equals the square root of 6 times f of 6 minus 9. We just calculated that f of 6 is 39. Substituting this value, we get g of 6 equals the square root of 6 times 39 minus 9. 6 times 9 is 234. So the expression becomes the square root of 234 minus 9. 234 minus 9 is 225. So we need to find the square root of 225. The square root of 225 is 15. The question specifies the positive value, so our answer is 15. This matches option D. To recap, we first solve the inner part, f of 6, and then use that value in the outer function, g of x. This is the standard procedure for evaluating composite functions. Our next problem is a practical application of percentages involving discounts and taxes. Laura has $100 to buy a perfume that is discounted by 25% but taxed at 6% as a luxury item. We need to find the most expensive original price of perfume she can afford. The objective here is to apply multiple percentage changes correctly to an unknown starting value. This requires careful algebraic setup to avoid common errors. Let's break this down. First, we need to apply the discount. An item discounted by 25% means you pay 75% of its original price. If P is the original price, the discounted price is 0.75 times P. So the discounted price is 0.75 times P, where P is the original price of the perfume. Next, we apply the sales tax. A 6% tax means the final cost will be 106% of the discounted price. Crucially, we apply the tax to the discounted price, not the original price. The final cost is 1.06 times the discounted price, which is 0.75 P. This simplifies to 0.795 P. Laura has $100, so her final cost cannot exceed this. We set up an inequality. The final cost, 0.795 P, must be less than or equal to $100. To find the maximum original price, P, we can treat this as an equation. 0.795 P equals 100. To solve for P, we divide both sides by 0.795. This gives us P equals approximately 125,786. The problem asks us to round to the nearest tenth. Looking at the hundreds place, 8 is greater than or equal to 5, so we round up. Rounding to the nearest tenth, the maximum original price P is $125.80. This corresponds to option B. A common mistake is to add the tax percentage to the discount percentage, which would be 25 plus 6 equals 31%. If you then apply a 31% discount to the original price, you get a different and incorrect result. Always apply discounts and taxes sequentially to the correct base amount. Our third problem involves working with ratios to determine ingredient quantities for a recipe. A cake recipe uses ingredients in the ratio of 5 to 10 to 5 to 3 to 2 for sugar, flour, egg whites, cocoa, and nuts. We need to find out how many pounds of cocoa are needed for a 75-pound cake. The objective here is to interpret a ratio and use it to find the fractional part of a whole. A ratio tells us the proportion of each ingredient relative to the others, but not the actual amounts. The first step is to find the total number of parts in the ratio. This represents the relative size of the entire cake. We sum the numbers in the ratio. 5 plus 10 plus 5 plus 3 plus 2 equals 25 parts. This means the entire cake is made up of 25 relative parts. Next, we need to identify the part of the ratio that corresponds to cocoa. Cocoa is the fourth ingredient listed, and the fourth number in the ratio is 3. So 3 parts of our cake are cocoa. Now we can determine what fraction of the whole cake is made of cocoa. This fraction is the number of cocoa parts divided by the total number of parts. The fraction of the cake that is cocoa is 3 divided by 25. This means that cocoa makes up 3/25 of the total weight of the cake. Finally, to find the actual weight of cocoa needed, we multiply this fraction by the total weight of the cake, which is 75 pounds. The weight of cocoa is 3/25 of 75 pounds. We calculate this as 3 times 75, all divided by 25. 225 divided by 25 gives us 9. So 9 pounds of cocoa are needed for a 75-pound cake. This is option C. To quickly review the process, We first found the total number of ratio parts, then identified the parts corresponding to the item we needed, which allowed us to form a fraction. We multiplied this fraction by the total quantity to get our final answer. Our fourth problem is a data interpretation question, common in the calculator section of tests. We have a graph showing the predicted stock price over 12 months as a line and the actual stock price as dots. The question asks for how many months the theoretical data predicted the stock price fairly accurately. The objective is to interpret graphical data and apply the subjective term fairly accurately to a scatter plot with a line of best fit. Since this is an SAT question, fairly accurately usually implies the dot is either on the line or very, very close to it. Let's examine the points month by month. We're looking for points that are extremely close to the line, or perfectly on it. The dot for month 1 is exactly on the line, at a price of $5, so that's 1 month. Month 2 is clearly above the line. Month 3 is also clearly below the line. Month 4 looks to be perfectly on the line, at about $8. That's a second month. Month 5 is significantly above the line. Month 6 appears to be perfectly on the line at $10. That's a third month. Month 7 is significantly above the line. Month 8 is significantly below. Month 9 looks to be perfectly on the line at $13. That's a fourth month. Months 10 and 11 are clearly below the line, and month 12 is significantly above. So we've identified 4 months where the actual price points appear to be exactly on the predicted line. The question asks for fairly accurately. There are no other points that are so close to the line that we could confidently say they are fairly accurate. In these types of problems, unless the point is nearly indistinguishable from the line, you should err on the side of caution and count it as inaccurate. Therefore, the answer is 4 months. This is option D. The months that fit this description are 1, 4, 6, and 9. A key takeaway here is to pay close attention to the wording in data interpretation questions. The term fairly accurately might seem subjective, but in the context of these tests, it usually implies a very close match. Problem 5 involves a function transformation, specifically a horizontal shift. We're given a function g of x equals 3x squared minus 28. We're also told that g of x minus a equals 3x squared plus 36 plus 80. Our goal is to find the value of the constant a. The objective is to understand how horizontal shifts work in functions and to use algebraic manipulation to compare two polynomial expressions. A horizontal shift of a units means replacing every x in the original function with a x cosh a. Let's start by calculating g of x minus a. We take the original function g of x and substitute xa in place of every x. So g of x minus a equals 3 times the quantity x minus a squared minus 28. This is our expression for the transformed function. Now we need to expand and simplify this expression to see what it looks like. We expand the squared term. xa squared is x squared minus 2x plus a squared. Distributing the 3 gives us 3x squared minus 6x plus 3a squared minus 28. The problem states that this expression is equal to 3x squared plus 36x plus 80. Let's set them equal to each other. We have the expanded form on the left and the given form on the right. Both expressions represent the exact same polynomial. For two polynomials to be equal, their coefficients for each power of x must be identical. Let's compare the coefficients of the x term. On the left, the coefficient of the x term is negative 6a. On the right, it's positive 36. Setting them equal, we get 6a equals 36. Now we can easily solve for a. Dividing both sides by 6, we find that a equals 6. To be thorough, let's also compare the constant terms to make sure our value of a is consistent. This is a good way to check your work. On the left, the constant term is 3a squared minus 28. On the right, it's 80. If a equals 6, then 3 times 6 squared minus 28 is 3 times 36 minus 28, which is 108 minus 28. And 108 minus 28 is 80. It matches, so our answer is correct. The value of a is 6, which is option B. Our sixth problem is a classic geometry question involving intersecting lines and angle relationships. We're shown 3 lines intersecting at a single point. 3 of the 6 angles formed are labeled x degrees, x minus 10 degrees, and x plus 25 degrees. Our task is to calculate the value of x. The objective is to recall and apply the key geometric theorems for angles formed by intersecting lines, specifically vertical angles and the sum of angles on a straight line. Let's use the property that the sum of the angles around a central point is 360 degrees. To do this, we need to know all 6 angles. Let's find the missing angles using the vertical angle theorem, which states that vertical angles are equal. The angle x plus 25 degrees is vertically opposite to the unlabeled angle below it. The angle x minus 10 degrees is vertically opposite to the unlabeled angle below it. And the angle x degrees is vertically opposite to the angle below it. So the 6 angles are x, x minus 10, x plus 25, and their vertical counterparts. Now we can sum all 6 angles and set the total equal to 360 degrees. The sum is x plus 25 plus x minus 10 plus x plus their vertical angles, x plus 25 plus x minus 10 plus x. This equals 360. Let's collect the like terms. There are 6 x terms, which combine to 6x. The constants are 25, minus 10, 25, and minus 10. This gives us a total of plus 30, so the equation is 6x plus 30 equals 360. Now we solve for x. Subtracting 30 from both sides gives us 6x equals 330. Dividing by 6, we find that x equals 55. Let's check the answer by plugging x equals 55 back into the original angles. The angles are 55 degrees, 45 degrees, and 80 degrees. The sum of these three angles is 180 degrees, which is correct for angles on a straight line. The sum of all 6 angles is 2 times 180, which is 360 degrees. Everything is consistent. The value of x is 55, which is option C. Problem 7 presents a double inequality with a specific condition. We need to find the perfect height n of a crash test dummy. We know n is an integer, divisible by 5, and falls within the range defined by the inequality is less than 3n, plus 11 is less than 245. Find n. Our objective is to solve a double inequality for a variable n, and then apply additional number theory constraints to find the specific integer value that fits all criteria. Let's start by solving the inequality for n. The first step is to isolate the term with n in it, 3n. We can do this by subtracting 11 from all three parts of the inequality, the left side, the middle, and the right side. This gives us 216 is less than 3n is less than 234. Now we need to isolate n. To do that, we divide all three parts by 3. 216 divided by 3 is 72. 234 divided by 3 is 78. So our inequality becomes 72 is less than n is less than 78. This means n must be an integer between 72 and 78, not including 72 or 78. Let's list the possible integer values for n. The integers in this range are 73, 74, 75, 76, and 77. Now we need to apply the additional conditions. The problem states that n must be an integer divisible by 5. Out of our list of possible values, only 75 is an integer that is divisible by 5. 75 divided by 5 is exactly 15, with no remainder. Therefore, the only value that satisfies all the conditions is n equals 75. This matches option D. The key to this problem was to handle the inequalities first, to get a range of values, and then use the other constraints to narrow that range down to a single correct answer. Always check all given conditions. Problem 8 involves comparing the volumes of a cube and a cylinder based on a set of relationships. We're given a set of relationships. The edge of a cube, L, is equal to the radius of the base of a cylinder, R. And the height of the cylinder, H, is 6 divided by pi times the cube's edge, L. We need to find the ratio of the cylinder's volume to the cube's volume. Our objective is to use a variable, express the volume formulas for both shapes in terms of that single variable, and then form a ratio to see what simplifies. Let's use R as our single variable for the radius of the cylinder. First, let's write down the volume of the cube. The volume of a cube is the edge length cubed L cubed. Since L equals R, we can write the cube's volume as R cubed. So the volume of the cube is R cubed. Now let's find the volume of the cylinder. The volume of a cylinder is pi times the radius squared times the height, or pi r squared h. We need to substitute both the radius and the height into the cylinder's volume formula, expressing everything in terms of r. Volume cylinder equals pi times r squared times the quantity 6 over pi times L. Since L equals r, we replace L with r. This gives us pi r squared times 6 over pi times r. Let's simplify this expression. The pi in the numerator and the pi in the denominator cancel each other out. We're left with 6 times r squared times r, which simplifies to 6r cubed. So, the volume of the cylinder is 6r cubed. Now we have both volumes in terms of the same variable r. Volume of cube is r cubed, and volume of cylinder is 6r cubed. The final step is to find the ratio of the cylinder's volume to the cube's volume. The ratio is 6r cubed divided by r cubed. The r cubed terms cancel out, leaving us with a ratio of 6. This is option B. The key here was to define all dimensions in terms of a single variable, r, and then substitute them into the volume formulas before simplifying. This ensured we were comparing like terms and allowed for cancellation. Problem 9 is a weighted average calculation, a common task in many areas of life, including academic grading. We have Avery's grades in a math class, 60 for the midterm, 90 for the final, 80 for a quiz, 100 for homework, and 100 for participation. The grading policy assigns a different weight or percentage to each component. We need to find Avery's final grade, which is the weighted average of these scores. The objective is to calculate a weighted average. This means each grade's contribution to the final average is determined by its weight, not just its value. It's not a simple arithmetic average. To calculate a weighted average, you multiply each score by its corresponding weight, then add up all these products, and finally divide by the sum of all the weights. The formula for a weighted average is the sum of weight times score divided by the sum of the weights. We need to make sure the weights are in their decimal form, so 30% becomes 0.3 and so on. Let's plug in Avery's scores and the given weights. Avery's final grade is 0.30 times 60, plus 0.40 times 90, plus 0.15 times 80, plus 0.10 times 100, plus 0.05 times 100. And we'll divide all of that by the sum of the weights, which is 1. Let's calculate each product in the numerator. 0.30 times 60 is 18, 0.40 times 90 is 36, 0.15 times 80 is 12, 0.10 times 100 is 10, and 0.05 times 100 is 5. Now let's sum them up. Adding these values together, 18 plus 36 plus 12 plus 10 plus 5 gives us a total of A1. The sum of the weights is 0.30 plus 0.40 plus 0.15 plus 0.1 plus 0.05, which equals 1. This means the percentages are correct and add up to 100%. So Avery's final grade is A1 divided by 1, which is A1. This is option D. This problem is a direct application of the weighted average formula. Just remember to convert percentages to decimals and to multiply each value by its weight before summing. Our final problem for this walkthrough is another data interpretation question, but this time from a bar graph. We have a bar graph showing the results of a standardized test in 2020. The problem states that the school district had the same total number of students, 650, in both 2019 and 2020. We're also given a fact about the 2019 scores. 15 more students scored in the 70 to 79 range than in the 90 to 100 range. The objective is to find how much this number increased in 2020, expressed in percentage points. The objective is to analyze data from a graph and compare it to a given statistic to find a percentage point change. This problem requires careful reading and attention to detail. Let's first understand the question. It's asking about the difference in the number of students between two score ranges, 70 to 79 and 90 to 100. Let's call this difference D. We need to calculate this difference D for both 2019 and 2020, and then find the percentage point increase. First, let's look at the 2019 data. We're explicitly given the difference. The problem states that in 2019, 15 more students were in the 70 to 79 range than the 90 to 100 range. So, the difference for 2019 D 2019 is 15. Now, let's find the difference for 2020. Using the bar graph, we need to read the approximate number of students from the graph. The bar for 70 to 79 goes up to about 110 students. The bar for 90 to 100 goes up to about 80 students. So, the difference for 2020 D 2020 is 110 minus 80, which is 30. The question asks for the change in percentage points, not a percentage increase of students. It wants to know how the difference D changed as a percentage of the total student body. So let's express both D 2019 and D 2020 as a percentage of the total 650 students. For 2019, 15 students is 15 divided by 650, which is about 2.31%. For 2020, 30 students is 30 divided by 650, which is about 4.2%. The change in percentage points is the difference between these two percentages. Change L's 4.62% minus 2.31%, which is approximately 2.31 percentage points. This doesn't match the options perfectly, which is often the case when reading approximations from a graph. Let's reread the question. It asks, by how much did that number increase? The most straightforward interpretation of that number is the difference, D. The change in the difference is 30 minus 15, which is 15. The number, difference, increased by 15. The question then asks for this change in percentage points. The increase of 15 students represents 15 divided by 650, which is approximately 2.3%. This still doesn't match the options. Let's reevaluate the most likely interpretation in a test setting. It often asks for the percentage increase in the difference, not the percentage point change. A percentage increase is calculated as the change divided by the original amount. The change is 15, and the original amount from 2019 is 15. So the percentage increase is 15 divided by 15, which is 100%. This matches option D. This problem highlights the importance of clarifying ambiguous wording on tests. When presented with choices, sometimes the intended question becomes clearer. Here, a percentage increase in the difference D makes more sense in the context of the answer options. Our 11th problem is a word problem that can be translated into a linear equation. A township has a $75 minimum fine for speeding. An additional $5 is added for every mile per hour a driver travels over the 25 mph speed limit. A driver was fined $250. We need to find the speed recorded by the police radar. The objective is to read a word problem, identify the unknown quantity, and set up an equation that models the given information. We'll use this equation to solve for the unknown. Let's define our variable. The question asks for the speed recorded by the radar. Let's use the variable s to represent the speed in miles per hour that the radar recorded. The additional fine is based on how much the driver was exceeding the speed limit. The limit is 25 mph. So, the number of miles per hour over the limit is the recorded speed, s minus 25. The additional fine is $5 for each of these miles per hour. The additional fine is $5 times the quantity s minus 20. The total fine is the sum of the minimum fine and the additional fine, and we know the total is $250. So, our equation is 75, the minimum fine, plus 5 times the quantity s minus 25 equals 250, the total fine. Now we just need to solve this equation for s. Let's start by isolating the term with the variable. Subtract 75 from both sides. 250 minus 75 is 175, so 5 times s minus 25 equals 175. Next, divide both sides by 5. 175 divided by 5 is 35. This leaves us with s minus 25 equals 35. Finally, add 25 to both sides to solve for s. 35 plus 25 is 60. So, the speed recorded by the police radar was 60 miles per hour. This is option A. The most crucial step in problems like this is correctly translating the words into a mathematical equation. Once you have the right setup, the algebra is straightforward. A quick check? If the speed is 60 mph, that's 35 mph over the limit. 35 mph times $5 per amp is $175. Add the $75 base fine, and you get $250, which is correct. Problem 12 is a direct test of your ability to translate algebraic expressions into their English word descriptions. We need to find the accurate description of the expression 17 minus 2z over 3. The objective is to correctly identify the components of an algebraic expression and represent the mathematical operations using appropriate English phrases. Let's break down the expression piece by piece. We have 17, and we are subtracting something from it. This means we are starting with 17 and taking something away. The part being subtracted is 2z over 3. The fraction bar means division, so this is 2z divided by 3, and 2z means 2 times z. So we are subtracting 2/3 of z from 17. Let's put that all together. We are taking 2/3 of z and subtracting it from 17. A direct translation is 17 less 2/3 of z. Let's see which option matches this or is equivalent. Option C says 2/3 of z less than 17. This is equivalent to our translation. The phrase a less than b means b minus a. So 2/3 of z less than 17 means 17 minus 2 over 3. This is a perfect match. Let's quickly check the other options to see why they are incorrect. Option A, 17 increased by 2/3 of z, would be 17 plus 2z over 3. Incorrect. Option B, 2 over 3 of z increased by 17, would also be 2z over 3 plus 17, or 17 plus 2z over 3. Incorrect. Option D is 17 more than 2/3 of z is equivalent to option A and B. Incorrect. So the correct answer is C. The key is to correctly interpret the phrase less than as subtraction, and to remember that the order is reversed in that construction. Problem 13 is about quadratic equations and the relationship between roots and coefficients. We have a quadratic equation. X squared plus mx plus n equals 0. We're told it has two real solutions, or roots, x equals 2 and x equals 3. Our task is to calculate the values of the coefficients m and n. The objective is to apply the relationships between the roots of a polynomial equation and its coefficients. For a quadratic equation, there are simple formulas connecting the sum and product of the roots to the coefficients m and n. These relationships are very useful for problems like this. For a quadratic equation in the form x squared plus bx plus c equals 0, the sum of the roots is b over a, and the product of the roots is c over a. For our equation, x squared plus mx plus n equals 0, we can identify a as 1, b as m, and c as n. This means the sum of our roots should be negative m, and the product of our roots should be positive n. Now let's use the given roots 2 and 3. First, let's find the sum of the roots. 2 plus 3 is 1. We know the sum of the roots is also equal to cosh m, so m equals 1. This means that the coefficient m must be positive 1. Now let's do the same for the product of the roots. The product of the roots is 2 times 3, which is 6. We know the product of the roots is also equal to n, so n must be 6. So we found that m equals 1 and n equals 6. This matches option D. Let's review. Instead of plugging in each root and solving a system of equations, we used the fundamental relationship that the sum of the roots of a quadratic is negative b over a, and the product of the roots is c over a. This is a powerful and efficient method for solving this type of problem. Problem 14 is a coordinate geometry problem involving a midpoint. We have a line segment AB. The point C is the midpoint of this segment. We are given the coordinates of A as 2 to 1 and the coordinates of C as 0, 1. We need to calculate the coordinates of point B. The objective is to apply the midpoint formula in reverse. The midpoint formula gives you the coordinates of the midpoint if you have the two endpoints. Here we have an endpoint and the midpoint, and we need to find the other endpoint. The midpoint formula states that the coordinates of the midpoint, xm, ym, are the average of the endpoint coordinates, x1, y1, and x2, y2. The x-coordinate of the midpoint is x1 plus x2 divided by 2, and the y-coordinate of the midpoint is y1 plus y2 divided by 2. Let's plug in the coordinates we know. Let A be x1, y1 equals y2, 1, and let the midpoint C be xm, y2 equal 0, 1. We are looking for B equals x2, y2. We can set up two separate equations, one for the x-coordinate and one for the y-coordinate. For the x-coordinate, 0 equals 2 plus x2 divided by 2. For the y-coordinate, 1 equals 1 plus y2 divided by 2. Now let's solve the first equation for x2. First, multiply both sides by 2. 2 times 0 is 0. So 0 equals 2 plus x2. To solve for x2, add 2 to both sides. We find that x2 equals 2. Next, let's solve the second equation for y2. First, multiply both sides by 2. 2 times 1 is 2, so 2 equals 1 plus y2. To solve for y2, add 1 to both sides. We find that y2 equals 3, so the coordinates of point B are 2, 3. This matches option B. To check, we can calculate the midpoint of A2, so 1, and B2, 3. 2, 2, 2, 3, 2, which is 0, 2, 2, 2, or 0, 1. This is exactly the given point C, so our answer is correct. Problem 15 requires us to interpret a graph to count the number of real roots of a function over a specific interval. We're shown the graph of the function f of x equals cosine of x minus 2. We need to determine how many real roots the function has in the open interval from x equals 5 to x equals 5. The objective is to understand what real roots are in a graphical context, and to identify them on the given graph within a specified interval. A real root of a function is any x value where the function's output y is 0. Graphically, real roots are the points where the function's curve crosses the x-axis. The problem asks for roots within the open interval, 5 to 5. This means we are only looking at the section of the graph between the vertical lines at x equals 5 and x equals 5. We do not include the points at x is 5 or x5 themselves. Let's visually scan the graph within this interval and count how many times the curve intersects the horizontal x-axis. Starting from x equals 5, we can see one point where the curve crosses the x-axis. That's one root. As we move to the right, we see another crossing. That's 2 roots. And a bit further, we find a third crossing. That's 3 roots. So counting the intersections, we find there are 3 roots. The graph shows 3 x-intercepts between x equals 5 and x equals 5. So the function has 3 real roots in this interval. This corresponds to option A. A common mistake is to misinterpret roots, or to accidentally count intersections outside the specified interval. Always make sure to look only at the relevant section of the graph as defined by the inequalities. You could also solve this algebraically, but interpreting the graph is generally faster for these types of questions, especially when using a calculator. Our final problem, number 18, is a logical reasoning question involving inequalities. We are given 2 inequalities. M is less than 7, and n is less than 3. We need to determine which of 3 other inequalities must be true. The objective is to reason about the properties of inequalities. Must be true is a very strong condition. If you can find just one counterexample where the original conditions are met but the statement is false, then that statement does not must be true. Let's examine the first inequality. I sim plus n is greater than 0. We know m is less than 7 and n is less than 3. This means m could be a large negative number, like 100. If m is 100 and n is 1, then m plus n is 99, which is not greater than 0. This is a counterexample. Therefore, m plus n is not necessarily greater than 0. Now let's examine the second inequality. 2, n minus m is greater than 0. This inequality is equivalent to n is greater than m. We know m is less than 7, so m can be any number smaller than 7. And n is less than 3, so n can be any number smaller than 3. We can easily find a counterexample. Let m be 0 and n be 5. Both satisfy the original conditions. But n minus m is 5 minus 0, which is 5, and 5 is not greater than 0. So statement 2 is not necessarily true. Now let's look at the third inequality. m plus n is greater than 10. Let's try to find a counterexample. Could m plus n be 10 or less? Let's pick the largest possible values that do not satisfy the original inequalities. For example, if m is close to 7, say 6.9, and n is close to 3, say 2.9, their sum is 9.8. This is less than 10. You could try m6 and n for 2. Their sum is 8, which is less than 10. Since m and n must be smaller than 7 and 3, their sum must always be smaller than 7 plus 3, which is 10. Therefore, m plus n is not greater than 10. It must be less than 10. Let's re-examine the question and my options. I see. This problem was slightly different from what I described for option 3. The third inequality was actually m plus n is greater than 10. My reasoning showed that it is not true. Since we've shown that both statement I, 2, and 3 are not necessarily true, this indicates there might be an issue with the problem itself, or I have misread it. Let's reread the options given in the image. The options are phi only, I and 3 only, 2 and 3 only, and n 2 only. Given my analysis, none of these options appear to be correct. If the question intended for one of these to be the answer, it would typically involve an operation where the direction of the inequality is preserved or reversed in a predictable way. Let's consider a scenario where one of these could be true. For example, if the question asked what must be true about my nm, we can say that nm must be less than 3 can m. Since m7, we know m7. So n must be less than 3 is m, which in turn must be less than 3, 7, or 10. So n mitatu man senten must be true. But that's not what's asked. Given that standard SAT-style questions always have a unique correct answer from the provided options, and my logical counterexamples for I, 2, and 3 hold, there is a strong possibility of an error in either the question or the provided options for problem 16. In a real test, if you're confident in your reasoning and find no correct answer, it's best to flag the question and move on. That concludes our walkthrough of these math problems. We've tackled a range of topics, from composite functions and percentages to geometry and data analysis. Remember, the key to success on these types of problems is not just knowing the formulas, but also understanding when and how to apply them. Take your time to read the question carefully, break it down into smaller parts, and don't be afraid to use mental or written counterexamples to check must-be-true statements. Keep practicing, and your ability to approach and solve these problems will become second nature. Great work, and I'll see you next time.